Well, very good morning to all of you. So, what we were doing till the last class was I was trying to define a set of nomenclatures to you, or I was trying to unify all the nomenclatures that will be coming. And so, first I had defined a large number of nomenclatures which we have also encountered in our study of single phase flows. Just the total numbers of parameters are more here, and as usual I have defined the phase properties by denoting them with subscripts of 1, 2. For the total property or the mixture property, it is Tp and subscript Tp. In several books you can find M as the subscript, but usually I prefer it as Tp. Okay, and friends, interfacial, I is the subscript. In that way we had defined. After that we had also defined a few properties which I do not know whether we have it here or not. Yeah, a few properties which were unique to two phase flow situations. Okay, I have almost completed this particular portion. The only thing which is left till now is three properties I would like to define. Volume flux, of course, I have already defined. So, it is the volume flux, drift velocity and drift flux. Normally we will not be using these things, but for special models probably we will be using these particular situations. Okay. So, there are three properties which volume flux, of course, I had already defined. Then it is the drift velocity, and it is the drift flux. Okay. These three properties were the properties which we will be defining, and then we are going to finish this nomenclature. We will be going for the analysis part. Now, as far as the volume flux is concerned, as we have already defined, it is simply the volume flow rate per unit area. This I have already told you, and this is J equals to Q by A. Usually it is the average J that we find, and for two phase flow situations, naturally for everything we have to give certain subscripts. So, it is J1 which is equal to Q1 by A, J2 equals to Q2 by A. Okay. Now, all these things, they denote the average volumetric flux. When there is no variation across the cross section, then naturally the local flux and the average flux, they are the same. Okay. And so, therefore, under normal circumstances we are not going to put these brackets every time. It is implied that when we are speaking about the average fluxes, and under normal circumstances, since we will be dealing mostly with one dimensional flow situations, our local fluxes and the average fluxes are going to be the same thing. So, they denote the, basically whenever we put those brackets, just like single phase flow situations, they usually denote the cross sectional average values. Okay. And usually we omit them, and there are certain other things. For example, how are these component fluxes related to your local component concentration as well as the local velocity? That means local component concentration means alpha and local velocity u. How are J1, J2 related to the alpha and u1, u2? Okay. So, therefore, just from the definition you can know that since your J1 is nothing but Q1 by A, and your U1 is nothing but Q1 by A1, which is in other words Q1 by A into 1 minus alpha. So, therefore, from here we know very well that J1 it is nothing but 1 minus alpha into U1, J2 is alpha into U2. Right. So, this is the relationship between the volumetric flux and the local component concentration and the local component velocities. Okay. And how are they related to your, instead of alpha, how is it related to beta? Any idea how is it related to beta? j into 1 minus beta. Please come prepared with the nomenclatures, otherwise it is going to be difficult, and this is equal to j beta, isn't it? It is just the inlet flux, okay. Or in other words, suppose I would like to relate the mass flux and the volume flux. So, how are these two related, the mass flux and the volume flux? We know this is nothing but equal to g into 1 minus x by rho 1, yes or no? Okay, because we know q1 is nothing but w1 by rho 1, which is nothing but g1 a by rho 1, or in other words this is g into 1 minus x by rho 1, and therefore j1 is nothing but q1 by a, sorry, yeah. So, this is going to be g into 1 minus x by rho 1. Similarly, j2 equals to gx by rho 2. Okay. So, therefore, this relationship, this relates your the overall mass flux and the the component volumetric fluxes. Okay. So, by this relation we have related the volumetric flux with the void fraction, volumetric flux with the inlet void fraction or the inlet volumetric composition, and this is volumetric flux with the total mass flux. Okay. Or in other words, with the component fluxes, if you see how the volumetric fluxes and the mass fluxes of individual components are related, that is quite natural. It is nothing but g1 equals to rho 1. They are simply by substituting whatever we have learned. Okay. But remember one thing, usually we can write it down as q1 equals to j1 dA, sorry j1 into a, but the accurate expression is going to be something of this sort when there is a cross sectional variation of the void fraction q2. Naturally, in the same way we can write it in this particular manner. Okay. When j1, j2 vary across the cross section, we can write it in this particular way. So, these are the relationships which relate your component mass fluxes and the component volumetric fluxes. Whenever you are given any particular derivation, please start from the basic definitions and then start deriving. It is going to be easier for you. And as far as I am concerned, if you just start midway and then do something, some marks will be deducted. Okay, that you keep in mind. Well, so therefore, in the similar way, suppose we would like to relate say j1 by j2 with the slip ratio or the slip velocity, whatever it is. So, therefore, this is nothing but equal to q1 by q2, agreed, and this is again nothing, q1 as I have already written down here, I have written down q1, it can be written down as a into 1 minus alpha into u1. Okay. So, if we write it down in this particular manner and we substitute it, then we know that this is equal to u1 by u2 into 1 minus alpha by alpha, isn't it? So, therefore, in this particular way, or in other words, this is simply k into 1 minus alpha by alpha, where k is the slip ratio. Why we are trying to connect all these things? Because this is a measurable parameter. So, therefore, if we can connect, then if data are available on alpha, we can find out k, or the vice versa. Okay. Now, this was about the volume flux. Volume flux also probably you have heard. Two other terms, they come up just because of the different velocities the two phases have. Now, these two are the drift velocity and the drift flux. Now, the drift velocity, if you take it up, drift velocity, it is nothing but equal to this is nothing but equal to the component velocity minus the average velocity. Okay. So, what is the component velocity? How do we denote the component velocity? What is the nomenclature that I have used for the component velocity? u1 and the average is nothing but equal to j. Okay. So, the drift velocity it can be defined as u1j, this is equal to u1 minus j, u2j, this is equal to u2 minus j. Okay. Now, next comes the drift flux. Now, the definition of drift flux, this is the volumetric flux of either component. These definitions you will get in Wallace or Collier, any particular book you are going to get these definitions. Volumetric flux of either component relative to a surface moving at volumetric average velocity. This is the actual definition. Okay. So, volumetric flux of either component relative to a surface moving at the volumetric average velocity. So, mathematically how we can define this? This can be defined, is usually taken as J21, okay, and this is, as I have told you, volumetric flux of either of the component. What is the volumetric flux of either of the component? Say it is alpha into u2 minus alpha into j. So, therefore, it is alpha into u2 minus j. This is J21 and J12 equals to 1 minus alpha into u1 minus j. So, these three are the definitions which I wanted to say. Volume flux I have already told you, and after that it is the drift velocity. The drift velocity, which is nothing but the component average velocity, the component velocity minus the average velocity, and then is the drift flux, which we have defined it as the volumetric flux of either component relative to a surface moving at the average velocity. Now, remember one thing, this drift flux is very important. In fact, we will be developing a drift flux model using this particular concept. Okay, so, therefore, it is quite important. Now, this drift flux it arises just because the two fluids are flowing at different velocities. All these relative things, the slip ratio, the relative velocity, the drift flux, the drift velocity, everything arises just because the two fluids or the two phases are at different velocities, isn't it? So, therefore, we would like to derive or we would like to obtain expressions relating the drift flux and the relative velocity, and also we would like to see what is the relationship between J21 and J12. This is also another thing which we would like to see. Okay. Why? Because just we know that for relative velocity, what do we know? We know u21 equals to minus u12, that we know. Similarly, what is the relationship between these two? And definitely how is, because J21 arises as a result of say relative velocity. So, how is J21 related to K21? This is the thing which we would like to find out. Now, again let us start from the basic definition and let us see how we can do it. J21, as I have already defined, it is alpha into u2 minus j. Okay. We can just write it down as alpha u2 minus alpha j, isn't it? This j is nothing but j1 plus j2. Okay. So, therefore, this can be written down as alpha j1 minus alpha j2. Okay. Or in other words, we can write it down as y plus, this is minus alpha j. So, j is j1 plus j2, accordingly I have written it down in this particular fashion. Okay. So, therefore, this can be written down as in that words with this alpha u2, this can be written down as alpha into j2 by alpha, isn't it, minus alpha j1 minus alpha j2. Okay. So, therefore, we can write it down as, I will just repeat the expression once more here, j21 this was equal to j2 minus alpha j1 minus alpha j2. Okay. Or in other words, this is j2 into 1 minus alpha j1. Agreed? This is the relationship between the drift flux and the component volumetric fluxes. Agreed? Now, what about J12? 1 minus alpha into u1 minus j. Again, let us proceed in the similar fashion. Let us break it down. Then we get it in this particular form. Okay. And from here what we can do is, we can just write it down as j1 minus 1 minus alpha into j, which is nothing but equal to j1 minus 1 minus alpha into j1 plus j2. Okay. Or in other words, this can be written down as j12 can be written down as alpha j1 minus 1 minus alpha j2. Okay. Just compare this particular expression with this particular expression and tell me what is the relationship between j12 and j21. j12 equals to minus j21, isn't it? So, therefore, what do we arrive from here? We find out j12 equals to minus j21. This symmetry is very, very important. This should be kept in mind, and this remember, just like relative velocity, there is such a type of symmetrical relationship. So, when j21 increases, j12 decreases, and so on and so forth, they are equal in magnitude, but opposite in sign. So, therefore, if j12 acts in one particular direction, j21 is going to act in the other direction, just in opposite direction. They are equal in magnitude, but opposite in sign. Now, the relationship between the drift flux and the relative velocity. Okay. Again let us start from the basics. The basic equation j21, this is equal to, again let us start from the basic relationships. In the previous case, what we had done, we had substituted j as j1 plus j2, then we had substituted j1, j2, etc., and we had tried to do this. In this particular case, since we want to find a relationship between j21 and u21, naturally this j has to be substituted in terms of j1, j2, j1, j2 have then to be expressed in terms of u1, u2, and only after that we can get a relationship, otherwise it is not going to be possible. So, for this particular case, what we do, we can write it down just as alpha u2 minus alpha j1, same thing that we had done in the previously. Or in other words, this can be written as alpha u2, expressing j1 in terms of alpha, it is alpha into 1 minus alpha j1 minus alpha square u2, right. Or in other words, we can write it down as alpha into 1 minus alpha u2 minus u1. Agreed? Or in other words, we can write it down as alpha into 1 minus alpha u21. Understood? Where u21 is nothing but the relative velocity of phase 2 with respect to phase 1. So, from this particular expression, what do we get? We get j21 is proportional to u21, or in other words, inwards if we write it down, it is drift flux is proportional to relative velocity for a particular system under a particular condition. That means, we assume alpha to be constant. Okay. So, therefore, this is proportional to a relative velocity for a particular system under definite operating conditions. So, therefore, this thing has to be kept in mind. Drift flux, drift velocity we will be dealing in greater details when we will be doing the drift flux model, but this was all, and this completes the chapter of nomenclature. Okay. So, we had defined the set of nomenclatures. I would request you to revise the entire thing before we proceed further. Now, initially what we did, I tried to explain to you what is two-phase flow, why at all you have opted for this subject and why at all you should study this subject. Next, we had found out that the basic difference between single phase and two-phase flow arises just because the two phases, they have a wide variety of distributions. So, unless we understand the distributions, we cannot do much about it. So, we next took up a quite detailed description of the different flow patterns which are encountered during vapor liquid, gas liquid, liquid liquid, gas solid, as well as three phase flows, and also the changes which we encounter when the two phase flow situation encounters any sort of a pipe fitting, including bends, T junctions, contraction, expansion, orifice, and so on and so forth. Next, we started the analysis of two phase flows. Now, in order to analyze two phase flows, what I felt was initially we would have to cover the mostly the entire, definitely I could not cover the entire range of nomenclatures. Some things might come up in the process of discussing the analytical models which we will be discussing, but more or less the major set of nomenclatures which we are going to use. Now, after this it comes the analysis of two phase flows. How to analyze? It is nothing, it is just a fluid flow phenomena. Okay. So, therefore, it is going to obey the basic equations of two phase flow. So, we are going to do the same thing. Just like single phase flow, we will be writing the equation of continuity, equation of momentum, equation of energy. Energy equation I had forgotten to derive the first day. Today after the, just before the class ends, I am going to derive it for you. So, we have to write those three sets of equations, and then we have to apply suitable constitutive relationships, the boundary conditions, the initial conditions, and we have to solve them. Whatever you have done so far, the same thing we are going to do, just the number of equations are more. There we had one momentum equation. Here, if we have to consider the two phases separately, there has to be two momentum equations. If we consider a mixture of two phases, then definitely we will be having one momentum equation, but in that case that momentum equation will comprise of several mixture properties or two phase properties which are not easily measurable parameters. Okay. So, therefore, we need additional constitutive relationships to determine these mixture properties. Okay. And in this way the analysis of two phase flow will go on. Now, just like single phase flow, we would first like to discuss what are the different methods of analyzing two phase flow, and then depending upon the time available, we will be taking one model after the another. So, let us see the methods of analysis of two phase flow. Okay. So, just like single phase flow, when we do not understand anything of physics, we do not know what to do, what we do, we go for empirical correlations. And you know that even in single phase flow, there are several occasions where we use these empirical correlations. In fact, for turbulence, the number of empirical correlations are more. Most Bloch's equation and then the other equations to find out f as a function of Re, many of them are empirical equation. The very well known Dittus-Boelter equation is an empirical equation. So, when we do not understand the physics, when we do not know what to do about it, but we know that well this parameter is influenced by this set of parameters, then what we do? We try to derive a relationship between the output and the input parameters, either by some dimensional analysis or by grouping those parameters on the basis of some particular logic, and then the exact functional form between the input and the output is obtained, from a large amount of experimental data. This is a very common approach. So, naturally in two-phase flow also the simplest thing which we can do is empirical correlations, and some empirical correlations are very widely used. We will just be touching on those empirical correlations, because initially for everything there was lot of empiricism. Definitely I will not go for this. Just like in heat transfer you have to study Dittus-Boelter equation. So, in the same way in this particular case also, maybe the Lockhart and Martinelli correlation, which is a very well known correlation, maybe like that one or two correlations we will be touching upon. Okay. So, therefore, the basic thing which we usually do is that we are from the experiments which are used for investigating the phenomena, a large amount of experimental data are collected, and then based on this experimental data the empirical correlations, they are derived either by dimensional analysis or by grouping of several variables on a logical basis. Now, what are the main advantages of empirical correlation? Firstly, the main advantage is it is very simple to use, and the other thing is, without understanding the physics, more or less we can use it within a particular range of application. Whenever you use an empirical correlation, you will see there is a range of application which is given. Quite natural, beyond the range the physics changes, so the same particular correlation cannot be used. So, therefore, the main advantages of using this are, firstly it is easy to use, and secondly this can be quite accurate within the limits under which this has been developed. And what are the major disadvantages here? Since it is developed with very less insight into the physics of the flow, we do not have much idea how to improve the correlation. Okay. So, therefore, this is one of the major problems in using this particular correlation. And the second thing is, if we use it indiscriminately without using any logic, wherever we have a correlation, whenever you have to find out heat transfer coefficient, be it forced convection, be it free convection, use Dittus-Boelter. Will you get an accurate result? You are not going to get it. So, therefore, if used indiscriminately, then it can lead to several erroneous results. These things you already know, this is nothing special for two-phase flow. These are the problems inherent in empirical correlations itself. Okay. But nevertheless, when we cannot do anything, we resort to this. At least something is better than nothing, isn't it? Next, what we can do? Next is the simple analytical models. Okay. These simple analytical models, if you say, these models, they do not take into account the exact flow distribution, or they do not take into account the exact topology of the flow, but they can be very useful for organizing design or rather for predicting design parameters and with a minimum computational effort. Now, what are these simple analytical models? We assume some sort of a distribution. Say for example, we assume that the two phases are intimately mixed with one another. If that is the case, then the two phases do not manifest their presence separately while they are flowing. The entire thing manifests itself as a mixture with suitable average properties. So, we can treat the two-phase mixture as a single pseudo fluid with suitable average properties, and accordingly we can use simply single phase flow equations in order to predict the hydrodynamics of two-phase flow under homogeneous flow conditions. So, under the simple analytical models, the thing which we have is, firstly there are different distributions. We can assume that the two phases are intimately mixed. We can assume that they are totally separated and they interact just at the interface. These are the two extremes that we can assume. Okay. Accordingly, the simple analytical models, they can be include, one is the homogeneous flow model, and the other extreme we have is the separated flow model. Now, in homogeneous flow model, what we have done, we assume that the components, they are intimately mixed, so that none of them can manifest their properties separately, and therefore, the entire hydrodynamics can be predicted by suitable average properties. For under certain circumstances this can be very accurate. We will be dealing with the simple analytical models in much greater details, and you can very well understand that when it is a completely dispersed flow, okay, under that circumstances homogeneous flow model can give accurate results. But remember one thing, unless we have very high phase velocities, or at least one particular phase has a very high velocity, there will always be a slip which will be comparable to the mixture velocity. Okay. So, therefore, assuming that the two phases, see the first assumption when you make, when you are telling that the two phases are flowing as a pseudo fluid, is that the two phases are flowing at the same velocity. Moment the velocity becomes different, naturally they start manifesting their individual characteristics. So, therefore, the first thing is both of them are moving at the same velocity. Okay. But under normal circumstances, under practical applications, this happens under very few circumstances. For most of the cases there has to be a relative motion between the two phases. So, therefore, to improve the predictions of the homogeneous flow model, what we have to do? We have to incorporate the effect of this particular relative velocity and modify the expressions of the homogeneous flow model. Agreed? Now, for that what we can do? We incorporate the effect of relative motion by the concept of drift flux, and therefore, the improvement of the homogeneous flow model is the drift flux model, which is another, this drift flux model, this is an improvement of the homogeneous flow model which incorporates the relative motion between the two phases, and this is usually achieved by introducing the concept of drift flux, which we have done in such greater details just shortly, okay, and this will be discussed separately. So, therefore, generally these two, they are used for mixed flow and dispersed flow. If you remember the classification of flow pattern which I had done during my flow pattern discussion. At one extreme there was dispersed flow, the other extreme there was separated flow, and in the middle there was a range of mixed flow. So, for dispersed flow, for very high phase velocities, homogeneous flow model, but as the phase velocities start getting little less, then we find the slip comes in, and gradually even in dispersed flow the relative motion has to be included. Then when we enter the mixed flow regimes, at times it happens that if we incorporate the drift flux model, we get a much better prediction as compared to the homogeneous flow model, even if we have not considered the exact distribution. Just by considering the drift flux model, the predictions are improved drastically. Okay. So, therefore, drift flux model, it is of a greater applicability, and for a large number of occasions this is a very useful concept. And the other extreme what we have stratified flow, we have annular flow, where the two phases they do not mix at all. Definitely if you use say homogeneous flow model for it, you are not going to get very good results. That is quite an expected situation. So, for this particular case we have the separated flow model. Here what we do? We write separate continuity, separate momentum, separate energy equations for the two phases, and we take into account that the two phases they interact at the interface. If we do not consider the interactions, then we are just considering simply single phase flow of either of the phases. Definitely they will just be single phase flow equations, they will not be accurate. We do it under certain circumstances, but definitely the results are not very accurate, because unless we consider the interactions, it cannot be a two phase flow situation. So, therefore, for very accurate results or for reasonably accurate results, what we are supposed to do is, we are supposed to write down the equations of continuity, momentum, energy for the two phases, and we have to incorporate the interphasic interactions between them by using suitable constitutive relationships. So, these are the three simple analytical models. We will be dealing with all three of them in great details, and one by one we will be dealing with them, and then you will be understanding more about how we have incorporated the two phase flow characteristics into single phase flow equations and developed more or less accurate prediction results for predicting the hydrodynamics. We will basically be doing the hydrodynamics, and then if time permits we will go for the heat transfer characteristics as well. Okay. Now, after simple analytical models, the next thing which we have are integral analysis. Okay. Simply just like your single phase flow analysis. In single phase flow, where do we use this integral analysis? Any idea? What do we do in this integral analysis? We assume some form of distribution of concentration and some form of the distribution of your velocity profile, etc. Okay. And then after that, what we do? Exactly. So, integral analysis. In integral analysis, what do we do? Usually it is a one dimensional flow analysis, and what we do? We first assume certain functional forms. Certain functional forms, for example, for say velocity and concentration profiles. Okay. And then these particular functional forms, they are made to, these functional forms made to obey certain boundary conditions. Okay. And accordingly they are integrated and we get the total thing. This particular thing where we use it quite frequently in single phase flow analysis, we use them for the single phase boundary flow problems, isn't it? There we assume some sort of a parabolic profile or certain things for velocity, and accordingly after that we try to integrate that, assuming that r equals to 0, u equals to 0, r equals to capital R, u equals to u max or something. We integrate it and then we finally get the velocity profile. Okay. Same thing it happens here also. Okay. For more accurate analysis, what we do? After integral analysis, we go for the differential analysis. Here we have noted it down in the form of the increasing amount of complexities. So, in differential analysis, again the same thing we do. Velocity and concentration profiles, they are deduced from, not profiles, sorry, fields. Velocity and concentration fields, they are deduced from suitable differential equations. Okay. Then these suitable differential equations, we assume that they follow one dimensional flow idealization. They are written for time averaged quantities usually. Sometimes more sophisticated theories may even consider temporal variations. Okay. This we encounter in single phase theories of turbulence, this differential analysis. Okay. So, therefore, we find that this differential analysis, this is velocity, usually velocity and concentration, it is usually the one dimensional, both integral and differential analysis, we usually use it for one dimensional analysis. Okay. So, integral analysis, it is performed for two phase flow situations, just like it is performed for single phase flow situations by assuming certain functional forms which describe maybe the velocity or the concentration profiles. These functions, they are made to satisfy certain boundary conditions and then they are integrated and we get the entire profile. See, just as it has been done for single phase boundary flow problems. Differential analysis slightly more complex and more accurate. We assume the velocity and concentration fields which are deduced from suitable differential equations, and then usually we assume time averaged quantities, but temporal variations can also be considered for more sophisticated theories. And just if we draw analogy, we use this for single phase theories of turbulence. The next thing which we usually do, which I forgot to mention here, that is the flow regime based models. See, so far whatever we were discussing, we were not considering the exact topology of distribution. Empirical correlation, we were not considering anything. Homogeneous flow theory, we assume that they are intimately mixed. Okay. Next, your integral analysis, differential analysis, we are not exactly considering how the two phases are distributed. So, therefore, the next approach which I forgot to mention in my slide, it is the flow regime based models. Here what we do, we consider the exact flow distribution, how the two phases they are distributed. Accordingly, seeing the flow distribution, we write the equations of the conservation equations, equations of continuity, momentum, energy, etc., etc. Then we solve them. Depending upon the topology, we decide the boundary conditions, we apply them, and then we try to solve them. So, this is a much more logical approach. Okay. Now, remember one thing, usually what is our approach? Just like single phase flow theory, what we would like to do, we would like to take up, say, a more or less simplified thing, maybe simple analytical models. Okay. There, using more complex theories, we would like to introduce suitable correction factors or modifications to that particular theory, so that the predictions are improved. Okay. Now, these correction factors, these particular modifications, they can be obtained empirically as well if we really do not know the physics, how to incorporate them. For example, in the churn flow situation, we hardly know anything about the physics, it is so random, so chaotic. There probably if you have to, maybe we have derived a model and we find that it's not very well predicting the experimental results, but if we increase the values by say a factor of k or something, it's better. We do not have any clue of how to predict k. What we do, we take a large number of experimental data, we run them, and nowadays we have got many other good things. We have ANN, genetic algorithm, and those things. So, we can run them, and we can find that, well, with this particular range of data over this particular range, this value of k as a correction factor, if it is included, then the predictions are much improved, isn't it? So, those things either we can take them from empiricism if nothing is available, or we can use more sophisticated theories to incorporate them. So, then the chances of improved prediction increases. Okay. So, usually it is sort of a pyramidal sort of a thing, where the simplest thing is at the base, and gradually we go to more and more sophisticated things, and usually the more sophisticated models are usually, they are not used as such, they are used just as a tool to improve the prediction of the simpler models. So, that is a much more logical approach, because if we use differential analysis or maybe more and more complex things, maybe the computation etc., they become so difficult that it becomes unmanageable for us. So, usually we do not go for that. Okay. The thing which I have written here is the multi-scale analysis. This multi-scale analysis is, again, you consider all the types of variations, whatever variations are going in different scales, and you try to do it. So, usually our approach will be that we will try to keep the model as simple as possible, and then we would try to introduce correction factors or modifications as the case may be. Maybe for those particular things we will consider the physics, and we will use the more complex models to improve the predictions of the our simple models. Okay. And then I have mentioned one more thing, which is the universal phenomena. Here in the slide I have mentioned this is nothing, it is a class of very powerful techniques which is based on universal phenomena that are independent of flow regime, analytical model, or the particular system also. Okay. Typical examples may be the various theories of say wave motion, or the extremum techniques for obtaining the locus of limiting behavior of a system, and so on and so forth. This we generally we shall not be dealing with this much in our present course. Okay. So, well, with this particular thing I am going to end the basic introduction to two-phase flow. Okay. Whatever I had as an introduction to two-phase flow, that I am going to end, and we are going to start the simple analytical models. We will be starting with the homogeneous flow theory. Okay. And then gradually we will be going to drift flux model to the same. Before that, one thing I would like to do, I had told you that I had forgotten to mention, or rather to derive the energy equation. I had derived the I had derived the single phase equation of motion, momentum equation, isn't it? Energy equation is very simple. You tell me, when a fluid is flowing through a pipe, say water is flowing through the pipe, what are the different energy terms that we should be considering there? Before I end the class and I start the homogeneous flow theory, I would just like 1 or 2 lines, I will just derive it. Very true, it has to have, otherwise it cannot move. Potential energy, it must have a position of its own. Then since it is flowing, pressure energy has to be there, very correct. Then internal energy has to be there, and then if there is some amount of heat input, usually work done is 0. Okay. So therefore, we can write down the energy equation in this particular way. Say from one dimensional energy balance, say over a small length delta z, just like we had done for this. That same figure, if you remember, this same particular figure, we had taken a delta z, this same thing we are going to do, delta z of tube. So what are the different types of energy we have? PV, okay, this is the pressure energy, plus internal energy, plus this is for unit mass of the fluid that I am doing, okay, for one dimensional energy balance over small length delta z for unit mass of fluid. Let me mention it. Of tube, this should be here. For unit mass of fluid, this gives this thing. Internal energy, then this is nothing but kinetic energy, and we have the potential energy. Okay. This is equal to dq minus, this is, remember, capital Q is volume flow rate, this is small q. Okay. So this is the heat added, this is the work done. We never use it, just to denote it I have given a small w, because capital W is mass flow rate, but this, for most of the cases, this is equal to 0. Just to note one thing, all these d's I have written just d, and these d's are marked with dash. Those who have done my, I think none of you have done my thermodynamics class, then you would have understood I am very, very fussy about differentiating between inexact and exact differentials. Okay. So therefore, just note this thing. Okay. So where this V, as you know, this is nothing but equal to 1 by rho. Okay. So therefore, this is the total energy balance equation which you can write down for a single phase flow situation. Okay. Now here we know what is this du equal to, the internal energy. We can do two things. One is we can combine this two and we can write it down as du plus dpv dh. Okay. This is one thing. The other thing is we can also express du as dq plus df minus pdv, okay, where this df, it arises from irreversible friction losses. Okay. So therefore, these three are the components of du. Now if we substitute this particular equation in the basic energy balance equation, then what do we get? If in this particular equation, instead of this du, we write it down as, say, dq, let me do it, is it getting very messed up? Leave it, I'll rewrite it once more. So what I had written it down, dpv plus, instead of du, I will be writing dq plus df minus pdv plus d of half u square, sorry, this is the small u, plus dg sin theta z equals to dq. These cancel out. This can be written down as vdp plus pdv. So these also cancel out, and finally what we get? We get an expression as V dP plus U du plus G sin theta dz plus df equal to 0, right. You also must have obtained the same particular derivation, or in other words, if you divide throughout by dz, we get something like, see if you are getting this or not, minus dp dz, we take dp dz to this particular site, then we get minus dp dz, we can divide throughout by v, or in other words v is nothing but 1 by rho. So, therefore, this becomes rho df dz plus rho u du plus rho g sin theta. Yes or no? Okay, fine. Now, if we compare this particular expression, what is this rho u equals to? It is nothing but g. Now, if you remember from momentum equation, the final expression which we had obtained, what was it? It was minus dp dz equals to tau w s by a plus g du dz plus rho g sin theta. Remember, from the basic momentum equation we had derived this. So, therefore, if both of them are the pressure if both of them express pressure gradient, right, and pressure is the property of the system, then therefore, each term must be corresponding to one another. So, therefore, we find that all the terms are corresponding except this term and this term. Okay. This gives you the wall friction, and this, as I have told you, F is nothing but the irreversible frictional losses. From where does the irreversible frictional losses come? When only a single phase fluid is flowing through water, flowing through a pipe, naturally from the friction, nothing else. So, therefore, it is quite obvious that these irreversible pressure losses, they arise due to the friction, and therefore, rho df dz is equal to tau w s by a. For single phase flow, it is not a problem. But remember one thing, when we go for two phase flow situation, even under homogeneous flow condition, irreversible frictional losses will arise for the interaction between the two phases. So, therefore, this should comprise of the not only the friction between the wall and either of the fluid, but also between the fluid and the fluid. Okay. So, therefore, these two need not necessarily be equal for two phase flow situations, but they are definitely equal for single phase flow situations. Agreed? So, therefore, this completes everything that I had to tell you about the introductory portion of multi-phase flow. Okay. So, from the next class, we are going to start the homogeneous flow model. It is the simplest flow model, and you can very well expect what we are going to do there. Simply, we are going to write the single phase flow equations, maybe with average properties. But under that circumstance also, the situation will not be as simple as the single phase flow situation, even under such a simplified situation as well. So, we will be seeing what are the additional things that we have to consider even for the simplest case of two phase flows, and we will be proceeding accordingly. Okay. So, thank you very much.